Lecture 10-2, the step response and general solution of first-order circuits. The objective of this lecture is to describe how to analyze the step and natural response of first-order circuits that have either resistors and an inductor or resistors and a capacitor, and how we can use a general solution to find the step and the natural responses. As previously stated, the step response of an RL or RC circuit is the voltage or current that results when a DC source is suddenly added to a circuit. For the following example, we have a voltage source in series with a resistor and a capacitor, and the switch closes at time 0, and the capacitor starts to charge through the resistor. We will assume that V of 0 is equal to V naught, which is the initial voltage stored in the capacitor, and we're going to use KVL to derive the step response V of t for the circuit. We have also provided a sketch of the voltage across the capacitor so that you can understand how the time constants behave when you have a step response. So as the capacitor charges, it charges to the final value of Vs, which is the value of the voltage source. Notice that at one time constant, it is 0.632 times Vs, or at 63% of the final value. By 5 time constants, it should be within 1% of the final value. So we essentially use the 5 time constant mark to state where the capacitor has been fully charged and the circuit is now in its steady state response. So to solve this problem, the first thing we're going to do is to write the KVL equation after the switch closes. So now we will assume that we're at t equals 0 plus and the switch is closed. So the KVL equation is negative Vs, and we'll assume a clockwise current I, plus I times R, plus V of t, the voltage across the capacitor, is equal to 0. That's our first equation. Our second equation is that the current through the capacitor can be written as I of t equals C dV of t dt. Next, we're going to substitute equation 2 into equation 1, and we have negative Vs plus Rc dV of t dt plus V of t equals 0. And now I'm going to use Vs to the right side of the equation. So I have Rc dV of t dt plus V of t equals Vs. So now I'm going to subtract V of t, and I will have Rc dV of t dt equals Vs minus V of t. And just as we did before when we did the problems for the natural response, we're going to do separation of variables and write all the terms that have V of t on the left and everything else on the right. So when we do that, we have dV of t over V of t minus Vs, and that equals negative 1 over Rc dt. So next, to solve this differential equation, we're going to integrate the left and right side from 0 to t. So I'm going to integrate from 0 to t and from 0 to t. And when we do that, over here we get the natural log of V of t minus Vs evaluated from 0 to t, and this equals negative 1 over Rc times t. The left side of the equation becomes the natural log of V of t minus Vs divided by V of 0 minus Vs, and this equals negative 1 over Rc times t. So the way that we get rid of the natural log is we raise the left and right side of the equation to the e, and when we do that, over here we have V of t minus Vs over V of 0 minus Vs, and this equals e to the negative t over Rc. So the next thing we want to do is to solve this equation for V of t. When we do that, we get V of t is equal to Vs plus V of 0 minus Vs e to the negative t over Rc. This is our step response equation. And what you should notice here is that if the initial voltage across the capacitor is 0, it is consistent with the sketch we have here. V of t equals Vs minus Vs e to the negative t over tau, because the time constant tau is still R times C. Now let's do a similar derivation for an RL circuit. For the following circuit, assume I of 0 is equal to I naught and the switch closes at t equals 0. Use KCL to derive the step response I of t for the following circuit. So first, we close the circuit for t equals 0 plus. We mark the bottom node as ground, and we mark the top node as V of t. And we write the KCL equation. IS is equal to V of t over R plus I of t. That's our first equation. Our second equation is that V of t is equal to L di of t dt. So we're going to substitute equation 2 into equation 1, and we get IS equals L over R di of t dt plus I of t. So IS minus I of t is equal to L over R di of t dt. We're doing separation of variables again as we did before. So we get d I of t over I of t minus IS equals negative R over L dt. So then, just as we did before, the next thing we do is we integrate the left and right side from 0 to t, which equals the natural log of I of t minus IS over I of 0 minus IS, and that equals negative R over L t. And our next step is to raise both sides to the e to get rid of the natural log. So this becomes I of t minus IS over I of 0 minus IS equals e to the negative R over LT. And we solve for I of t, and we get that I of t is equal to IS plus I of 0 minus IS e to the negative R over LT. This is the step response for an RL circuit, and you should notice that if the initial current is 0, it's the same as the equation and the graph that we have here. I of t equals IS minus e to the negative t over tau, and within 5 time constants, it should charge to our final value of IS, and the time constant is still L over R. So now that we have talked about how to find the step response and natural response for RC and RL circuits, let's talk about a general solution. A general solution for both of these types of circuits is given by the following. X of t is equal to x of infinity plus x of 0 minus x of infinity e to the negative t over tau. Or if you're starting at a time other than 0, x of t is equal to the final value of x plus x of t naught minus x, the final value, e to the negative t minus t naught over tau, where xf, or x of infinity, is the final value of the variable, and x of t naught is the initial value, or x of 0, of the variable, where our variable is either a voltage or a current. This could be a voltage or a current for an inductor, a capacitor, or a resistor. The complete response of a circuit can then be decomposed into the natural and the step response, as we've discussed before, where the natural response is due to the stored energy and the step response is due to the independent source being suddenly attached. So x of t would be the sum of the natural and the step response, where the natural response is x of t naught e to the negative t minus t naught over tau. And x of step response is the final value minus the final value times e to the negative t minus t naught over tau. The natural response eventually dies out, and the steady state component is the part that would remain. Therefore, the response can also be characterized by the temporary part and the permanent part. The temporary part is the transient response, and the permanent part is the steady state response. The transient response is the circuit's temporary response that will die out with time and is due to the initial conditions. And the steady state response is the behavior of the circuit after a long time after an external excitation such as adding a voltage or current source is applied, and that is due to the source. So another way of describing x of t is the sum of the transient and the steady state response, where the transient would be x of t naught minus xf e to the negative t minus t naught over tau, and the steady state response would simply be xf. To compute the step and natural response of circuits, use the following 5 steps. First, you identify the variables of interest, whether it's capacitor voltage, inductor current, resistor voltage or current. Then you determine the initial voltage or current for the capacitor or inductor. Step 3 is to calculate the final value of the variable as t approaches infinity. Calculate the time constant for the circuit right after switching occurs. So typically we've used t equals 0 plus. And finally, use the general formula to find the variable of interest. All right, let's look at an example. For the following circuit, the switch opens at t equals 0. Determine I of t and also make a sketch of I of t. So to analyze this problem, we draw the circuit 3 times. We draw it at t equals 0 minus, t equals 0 plus, and t equal infinity. At t equals 0 minus, the switch is closed. At t equals 0 plus, the switch is open. And at t equal infinity, the switch is open. At t equals 0 minus, we're going to assume that the circuit has been sitting here with the switch closed for a long time. So it's a DC steady state condition. And we would model the inductor as a wire. At t equals 0 plus, the inductor is now charging or discharging, and we use this circuit to find tau equal to L over the Thevenin equivalent resistance seen by the inductor. And over here, t equals infinity, we use this circuit to find the final value of the current through the inductor, I of infinity. And since it's been going for a long time, we also assume DC steady state conditions. We use t equals 0 minus to find the initial current through the inductor. So now our next step is to draw these 3 circuits. So I have the 5 ohm resistor. I have the switch that is now closed. The wire that represents the current through the inductor, that represents the short circuit inductor. The 10 ohm resistor. And the 3 amp current source. Then, after the switch opens, I have the 5 ohm resistor, the break where the switch is now open, the 1.5 Henry inductor, a 10 ohm resistor, and a 3 amp current source. At t equal infinity, I once again have the 5 ohm resistor, the switch is still open, a wire to represent the current through the inductor, which I now label the current I of infinity, a 10 ohm resistor, and a 3 amp current source. For the first circuit, I have this wire that shorts out the 5 ohm and the 10 ohm resistors. So current wants to follow the path of least resistance. So I of 0 is equal to 3 amps. For this middle circuit, I want to find the Thevenin equivalent resistance seen by the inductor. When we look for the Thevenin equivalent resistance, we always turn off any independent sources. The way that we turn off a current source is we model it as an open circuit. So I now have 5 ohms, 1.5 Henry, and 10 ohms. So you should see that the Thevenin equivalent resistance seen by the inductor is 5 plus 10, which is 15 ohms. So tau is equal to L over R Thevenin, or 1.5 over 15, which equals 0.1 seconds. At my I of infinity circuit, you should see here that I have 3 amps, which feeds a 10 ohm and a 5 ohm resistor, and the shorted inductor is in series with the 5 ohm resistor. So I of infinity is equal to the current through the 5 ohm resistor. If I use the current divider, that's 5 in parallel with 10 over 5 times 3. So I of infinity is equal to 2 amps. Finally, we are ready to write the equation for the current through the inductor and create our sketch. So I of t is equal to I of infinity plus I of 0 minus I of infinity e to the negative t over tau. So I of t is equal to 2 plus 3 minus 2 e to the negative t over tau. And finally, I of t is equal to 2 plus e to the negative 10t amps. And that's for t greater than or equal to 0. So when we make our sketch, the horizontal axis is time in seconds. The vertical axis is I of t in amps. The initial current is 3 amps. So we start here at 3 amps. The final current is 2 amps. So the inductor discharges from 3 to 2. And we estimate that it gets there in 5 time constants. So 5 tau is 0.5 seconds. All right, let's look at our final example for today's lecture. Example 4. For the following circuit, the switch closes at t equals 0. Determine V of t and I of t and make a sketch of the equations. So once again, we're going to analyze this circuit at 3 different times. T equals 0 minus, t equals 0 plus, and t equal infinity. T equals 0 minus, the switch is open. T equals 0 plus, the switch is closed. And t equal infinity, the switch is still closed. We assume that the switch has been open for a long time, so we have DC steady state conditions at t equals 0 minus. We assume that the switch has been closed for a long time at t equal infinity, so we have DC steady state conditions at t equal infinity. Remember, DC steady state means that the capacitor looks like an open switch or an open circuit. We use this initial circuit to find I of 0 minus. We use t equals 0 plus to find tau equal to R Thevenin times C. And we use t equal infinity to find V of infinity. And actually, the first one should have been V of 0 minus because this is a capacitor, not an inductor. Okay, so our first circuit, I'm only going to draw the part of the circuit that is relevant to the capacitor. So I have a 10-volt source in series with a 2 ohm resistor. And then I have a break for the capacitor, and that's V of 0 minus. So since there's no current flowing through the 2 ohm resistor, V of 0 minus is 10 volts. Then I have a circuit here. I have a 10-volt source, a 2 ohm resistor, a 6 ohm resistor, the 50-volt source, and the capacitor. That's 1/3 of the farad. Since I'm looking for R Thevenin, and we turn off independent sources to find R Thevenin, I'm going to replace both voltage sources with a short. And the capacitor is 1/3 of a farad. So I have 2 ohms and 6 ohms. So R Thevenin is equal to 2 in parallel with 6, which is 1.5 ohms. So tau is equal to R Thevenin times C, and tau is equal to 0.5 seconds. Now I draw the circuit at t equal infinity, and I get a 10-volt source, a 2-ohm resistor, a 6-ohm resistor, open circuit where the capacitor was, and the 50-volt source. And I label this break V of infinity. And I'm going to use KCL to solve this problem because that node is V of infinity. So I'm going to have V of infinity minus 10 over 2 plus V of infinity minus negative 50 over 6 equals 0. So V of infinity is equal to negative 5 volts. So now we make our equation. V of t equals V of infinity plus V of 0 minus V of infinity, e to the negative t over tau. So V of t is equal to negative 5 plus 10 minus negative 5, e to the negative t over 0.5. And finally, V of t equals negative 5 plus 15, e to the negative 2t volts for t greater than or equal to 0. So the current through the capacitor is I of t is equal to C dV of t dt. So I of t is equal to 1/3 times negative 30 e to the negative 2t. So this equals I of t equals negative 10 e to the negative 2t amps for t greater than or equal to 0. So now let's make two sketches. One of them is going to be V of t. Here's time in seconds and V of t in volts. It's going to start at 10 volts and go to negative 5 volts. And it's going to take 5 time constants to get there. So that is 2.5 seconds. Now we're going to do the current. I of t, we know that we start with an open circuit for a capacitor. So the initial current through the capacitor is 0 amps right here. Then at t equals 0, it jumps down to negative 10 amps, and then it dies off. And it also gets to the final value in 5 time constants, or 2.5 seconds. This concludes today's lecture on using the general solution in order to find the step response of RC and RL circuits.